To everyone, welcome to another talk in the plenary series of the Student Symposium in Combinatorics. Especially welcome to those just joining us for the plenary talks. As with all of the other talks, this conference could not have gone ahead without the sponsorship of Matrix, AustMS, AMSI, and UNSW Sydney. So we're very grateful to their support. Now I'll be introducing Corrine Yap, who is a fifth-year PhD candidate advised by Bhargav Narayanan. She works in discrete mathematics with a focus on problems that lie in the intersection of combinatorics and other areas, including probability, topology, and statistical physics. As well as being a wonderful mathematician, Corrine serves as a wonderful example of how a mathematician can find intersections with important areas outside of academia. Corrine is heavily involved in organizing in mathematics, including various teaching groups and the Rutgers University chapter of the Association for Women in Mathematics. Corrine's also a performer, having theatre performances at over 15 different venues, as well as a playwright, having written and performed in her own one-woman play, Uniform Convergence, which confronts obstacles faced by the intersection of gender and race in the world of mathematics. She's also an interesting and insightful follow on Twitter, not least of all because of the photos of her adorable cats. Corrine's joining us today from Banff, so hopefully she doesn't have too many intersections with the local bear population. Today, continuing on that theme of intersections, Corrine will be talking to us about intersections of statistical mechanics and combinatorics. Over to you, Corrine.
Great. Thank you so much, Jack, for that absolutely delightful introduction. All right, let me go ahead and share my screen. All right, things looking good so far. Okay, so I apologize in advance that you are seeing my face in two places. There isn't really a way around this for Zoom because of the way I'm sharing my screen. So hopefully this isn't too distracting for you. Okay, so I am talking about intersections of statistical mechanics and combinatorics, and this is a field that I have somewhat recently become very interested in. And so the goal for my talk today will just be to highlight some really cool problems that I find in this area. And I assume that most people are coming to this talk from a combinatorial background and maybe not so much from a statistical physics or statistical mechanics background. And so I also want to sort of advertise to you why I think a statistical mechanics perspective can be useful when solving combinatorial problems, and hopefully get you interested in studying this area a little bit in the future. But please feel free to interrupt with any questions if you have them. I'll be able to see them since I'm on two devices. I'll be able to see them if you type them in the chat or in the Q&A. And I've also told Jack that he's free to interrupt me with any questions during the talk if there's anything that needs to be clarified or anything. Okay, so let's go ahead and start. So let me make sure I've got my pointer here. 1 second. Okay, I'm seeing that you can't see my pointer on the screen. Let me get to the first slide and I'll make sure that I can draw this. So first of all, what is statistical mechanics? So I'll also refer to it as a statistical physics. Those two things mean the same thing. The tagline for this area is that we are essentially studying macroscopic properties of physical systems via their microscopic interactions. So in the physical sense, what do we mean? We're thinking about, let's say, a system of particles like gas particles or particles of matter of some sort. And maybe we want to determine some sort of global structure or property of them. And we're going to do that by studying what happens at sort of a local microscopic level. So some examples of macroscopic properties we might be interested in are things like phase transitions. So a phase transition sort of informally means what you might think of it. If you heard of these things in like a high school chemistry or physics class, you know, a transition from a solid to a liquid and a liquid to a gas, we can formalize that in a more mathematical way. and long-range correlations between like particles in our systems. If I know what's happening with a particle over on this side, can I say anything about the state of a particle on this end of the system? And the sorts of microscopic interactions we'll be studying are really nearest neighbor interactions. And this should give you the idea of modeling things as vertices on a graph, where these edges represent the different interactions that we're allowed to have. And so we're going to start studying these as more combinatorial systems by modeling them on graphs. And in particular, I'll introduce several examples of what's called a spin model on a graph. Physicists are mainly interested when the graph is a lattice, because this sort of structure of a lattice like ZD more accurately represents the sorts of systems of particles that physicists are interested in. But as combinatorialists, there's no reason we should restrict ourselves to lattices, and we're going to consider more general classes of graphs. So I think the best way to dive into this is just to look at some guiding examples. So the first example I'm going to give you is called the hardcore model. And this is a model where it might not seem so physically intuitive, but it's very clear once I go through it that there are certain combinatorial properties that we'll be interested in for this model. So let me now test out my pen. Okay, great. So what is the spin model setup that we have? Well, we start with some graph, and we're assigning spins to the vertices. So in the hardcore model, I'll just say my spins are the numbers 0 and 1. And what are the spin configurations of my graph? These are the different sort of configurations of particles that I can have. I'm going to say that they're the independent sets of my graph. If you're not familiar with an independent set, it's a subset of the vertices where there are no edges in the set, such that I does not contain edges. Contain any edges. Okay. And the independent set will be specified by which vertices are assigned spin 1. And the ones with spin 0, I'll say, are not in the independent set. Okay, so what is the physical meaning of this? Like in a graph, independent sets are interesting to people who study graphs. But why are physicists interested in these? This is sort of a discrete version of a continuous model called the hard sphere model. You can imagine that our vertices can represent particles of gas in a room. And we'll say that two vertices are connected by an edge if those particles overlap with one another. And what that means is that the particles can't take up the same physical space. You can imagine each particle as sort of a sphere, and we can't have this like physical spheres overlapping with one another. And so a configuration of gas particles in the room corresponds to a sphere packing of these spheres. And if we look at those spheres, and we pretend that those are just vertices, then that exactly corresponds to an independent set in the graph, where we don't have an edge if the spheres don't overlap with one another. So that's sort of a reason why like a structure like an independent set might be interesting to a physicist. Maybe don't ask me more questions about the physics intuition, because I myself do not have much of a physics background. So this is sort of the extent I can say being a non-physicist as why a theoretical physicist might be interested. Okay, but let's continue with the abstract mathematical setup. So this is what I have. And then I am interested in varying some parameter for this model. And for the hardcore model, let me do my pointer instead. The parameter I'm interested in is called the activity or the fugacity of the model, and it'll be denoted by this lambda, some positive real number. And the statistics of any spin system or any spin model are going to be the Gibbs measure and the partition function. So these are the two things that we're interested in studying for all of these different models. What is the Gibbs measure? It's a probability distribution that we impose on our spin configurations. And the idea is that to sort of model the different spin configurations that there can be, we're going to just sample them at random. And the randomness will be governed by a weight that we assign to each configuration. So it won't necessarily be equally likely that we see one configuration or any other configuration. We might weight certain configurations so that they're more or less likely than others. So the weight that I'm going to give here will be proportional to lambda to the size of the independent set. So for example, if lambda is some number that's greater than 1, then I'm biasing towards larger independent sets. And so my larger independent sets are going to be the things that I'm more likely to see, and the smaller independent sets will be less likely. And this partition function is basically just the denominator that I have to have here in order for this to be a probability distribution, right? I need all of these probabilities to sum to 1. And so another way I can write this is that the probability will be lambda to the size of I divided by ZG of lambda. I ran out of room over here. So this is what guarantees that all of these different probabilities sum to 1. And it's the sum of all the different weights of my configurations. And so you can already see that this partition function is sort of a weighted counting tool. It's a combinatorial property of our model, because it's counting all the different weights I'm assigning to the independent sets, and it's something that maybe as a combinatorialist, or if you studied any graph theory, you might recognize as something that graph theorists are interested in as well. So first, let me give a concrete example in case you're not familiar with this sort of setup. So suppose that G is just a 4 cycle. So I have 4 vertices and I have 4 edges here. And I've given you an example spin configuration. So I have 2 zeros over here and 2 ones over here. So you can see that these 2 vertices with spin 1 are an independent set because they don't induce any edge between them. And what are my different statistics that I'm studying? Okay, well, what is the weight of this configuration? There are 2 vertices in it, so the weight will just be lambda squared. So the probability that I see this particular spin configuration when I sample from my hardcore model is lambda squared over ZG of lambda. And the partition function is just if I look at all possible ways of assigning, of getting independent sets in this graph, then what's the sum of all those different weights? So this expression here is what I get. You can see that I have 2 independent sets of size 2. So I have this one, this pair of opposite vertices, and then this pair of opposite vertices. Those are both independent sets. I have 4 independent sets of just 1 vertex. So it's if I take each singleton, that by itself will be an independent set. And I have 1 independent set of size 0 because the empty set is an independent set. It has no edges in it. And you can check that I don't have any independent sets of size 3 or 4. If I take any set of 3 edges in this graph, or sorry, any set of 3 vertices in this graph, they will induce an edge in that set. So I can't have an independent set of size 3. Okay, so this partition function is just some expression in lambda. And if I plug in a particular value of lambda, I get some number out of it. But this might look familiar to you if you've done anything with graph theory before. So we can rewrite this partition function by the way that I just did in the previous page without really telling you, by grouping together the different lambda terms. So I can just group together all of the lambda to the k's. And then my coefficient of lambda to the k is the number of independent sets of size k. And in graph theory, this is something we call the independence polynomial of this graph. And this is something that just independently, there was no pun intended, okay, independently, graph theorists are interested in studying just without the context of the hardcore model. And in fact, going back to what I said about the counting problem, if we plug in lambda equals 1, then we're just summing up all of these I sub k's for all k's. And that's exactly the number of independent sets in our graph. So this is a combinatorial quantity that people are interested in studying. But the really cool thing about this is that we have two perspectives. We have the graph theory perspective and we have the statistical physics perspective. And so even though we can ask a question about this independence polynomial in graph theory, maybe there are some tools we can use in statistical physics to gain more insight into this problem. And that's exactly what we do. So here's an example of a question we can ask about the independence polynomial in independent sets. This is an example of a problem in extremal combinatorics. So let's fix some positive integers d and n. And I'm going to specify that I'm working with d-regular n vertex graphs. So if you're not familiar, d-regular means every vertex has d edges incident to it or adjacent to it. So which d-regular n vertex graph has the maximum number of independent sets? So if I remove this d-regular assumption, it's pretty trivial. Then I can just take the empty graph on n vertices, right? The way that you have the maximum number of subsets with no edges is if you have absolutely no edges in your graph. So adding this d-regular assumption makes it an interesting question. So what has been done on this problem? Well, the first result was by Jeff Kahn in 2001, who showed that if G is bipartite, then actually the maximizer is this graph, the complete bipartite graph KDD, and you can take n over 2d disjoint copies of that. So what does that look like? You have d vertices on each side, and you have all the edges between them, and you don't have any edges in each of the sides. So that's the complete bipartite graph. And you just take as many copies of this as you possibly can. So you have n over 2d copies. And we'll assume divisibility works out just because we're going to take n to be large enough. So if we have a bipartite graph, then this is the maximizer. This is the largest number of independent sets you can have. And this is pictures about to go away when I go to my next slide. So let me copy it. And the way that Jeff Kahn proved this result was by using something called the entropy method in combinatorics, which is something that also lies in the intersection of combinatorics and statistical physics and also comes from information theory. But what was really neat was that this statement was improved strictly within a statistical physics context. So let me paste my picture in case that's helpful for anyone. What Galvin and Tetley did in 2008 was they actually generalized this result by looking at it in the context of the hardcore model. Because if you'll remember, I said that this is the same as zg of 1 in the previous slide. And this would be the same as z kdd of 1 to the power n over 2d. So this is another way of writing the inequality that Jeff Kahn proved. And if you just take the logarithm of both sides, then you get what's written down here. So take log of both sides, and you divide out the n over 2d. So you get 1 over n on one side, 1 over 2d on the other. And what Galvin and Tetley did was they actually didn't just restrict themselves to lambda equals 1, but they proved this statement for all lambda. And Yufei Zhao in 2010 removed this bipartite assumption and just made the statement for all graphs, for all d-regular n vertex graphs G, that this was true. And later on, Davies, Jensen, Perkins, and Roberts actually proved an even stronger result that only makes sense in the context of statistical physics. This is something called the occupancy fraction. And I'm not going to define what it is because it requires a little bit more background. But this is a stronger statement that implies both of the previous ones. And it has specifically to do with statistics in the hardcore model. So sort of the takeaway that I want you to have here is that a statistical physics can actually help, perspective can help solve combinatorial problems and can sometimes even prove stronger results in that context than the original combinatorial results that we were hoping for. Okay, so now I want to go to a couple of other models and leave the hardcore model behind, but I'll pause if there are any questions. And I know that people won't be necessarily unmuting themselves to ask questions, but if you have anything in the chat, You can feel free to ask that now. And I'll pause maybe for a sufficiently awkward number of seconds. Okay.
I haven't seen anything in the chat. Do you reckon that counts as sufficiently awkward?
Yeah, I think it does. Okay, great. So now I'm going to go on to another example. So you can, if you want, you can clear your mind of this one. And this one is called the Ising model. And so this one may be less clear sort of with the combinatorial connections, but it maybe is more intuitive when you just think about like, what is a spin model on some graph? Because this is a very basic way of defining a spin model. Your spins are -1 and 1. And your spin configurations, now we're not requiring that they have any sort of graph structure. We're just saying, okay, every vertex gets a -1 or a 1 arbitrarily. Like you can assign them however you would like. They could all be -1s. They could be half -1s, half 1s, whatever you would like. Okay. Also, I enjoy what Mark wrote in the chat. There is yet another way of thinking about the independence polynomial. I have heard of this, the F polynomial of the independence complex. I won't talk about any topology, but I think that is another really cool way that you can have a different perspective on combinatorial problems, is from a topological perspective. So I appreciate the comment that you made, Mark. Okay, so let's look at the Ising model. So these are our spins and our spin configurations, but now we're going to be dealing with slightly different parameters. So one quantity I'll be interested in is this M of G sigma, which is the number of monochromatic edges in sigma. So that will be the number of edges that have the same spin at both endpoints. So here there are two different ways you can do that. You can either have a -1 at both ends or a 1 at both ends. And this will be sort of the energy of the configuration. And the parameter we're going to be playing with is beta, which will be the inverse temperature. So you can think about it literally as the inverse of the physical temperature. And we're only going to be considering beta positive real number. And this is what's called the ferromagnetic Ising model. You can also think about negative beta, which is called the anti-ferromagnetic model, but I won't be focusing on that here. Okay. And again, as before, we have the same two statistics that we're interested in, this Gibbs measure and this partition function. So now the probability that I see any given spin configuration is going to be proportional to e to the beta times m. And I'll give some intuition for how we can think about this, this weight in a couple of slides. But just, sort of take this as I'm giving it to you. And the partition function is the sum over all the different weights of all the different weights over all configurations as before. Okay, so before I give some intuition about this, let me just give a brief example to make sure we're all on the same page. Again, let's say G is a 4 cycle, and I have some assignment of 1s and -1s to my vertices. And I can calculate how many monochromatic edges do I have here. Well, I have a 1, 1 here, and I have a 1, 1 here. So I have 2 monochromatic edges. So my weight is going to be e to the 2 times beta. And I divide by my ZG of beta. And as we were doing before, we can compute the partition function by just looking at all possible spin configurations and computing the weight of those. So here you can see I have 2 configurations with weight 4. So there are 2 configurations with exactly 4 monochromatic edges. That would be if these were all 1s or all -1s. I have 12 configurations with 2 monochromatic edges. So I have all of these sort of 3 of the same spin. I could have all of those possible configurations. And then I could also have, for example, 1, 1 and -1, -1. And I could swap those. So I get those sorts of configurations as well. And then I have 2 configurations with no monochromatic edges, and that's if I have opposite corners having the same spin. Okay, so again, here's our partition function. And this is some expression now in e to the beta. So how should I think about this e to the beta, expression, and what is beta, the inverse temperature, doing here? Well, okay. One way that can help is first, we can generalize this model pretty naturally. If we think about our spins as colors instead, then this becomes a two coloring of our graph. And so we can generalize to something called the Potts model, where instead of -1 and 1, I have some finite set of spins, 1 through q. And then my spin configurations are q colorings of the vertices in my graph. And I have the same parameters as before, the exact same setup. And this is called the Potts model. And this is the model that I'll be talking about for the rest of the talk. And what is this beta doing with the Potts model? Okay, so we can think about two different regimes for a Potts model. There's sort of a high temperature regime and a low temperature regime. So remember, beta is inverse temperature. So high temperature means beta is small. And what's our physical intuition? Well, when we have some sort of matter at high temperature, what's going on? We should think about it like a gas. And what's happening with gas particles? They're sort of disordered and chaotic. There's no structure that you can there's no large overarching structure you can discern about the configuration. And you don't really have long range correlations. Like if you know that one particle is doing something over here, you can't really say what some other particle is doing over here based on what you know. And we can see that that's the case when we sample from the Potts model for small beta. And in fact, that's reflected in our Gibbs measure, because remember, mu g of q beta, or sorry, mu g of, not q beta, of sigma is proportional to e to the beta times the number of monochromatic edges. And so just sort of heuristically, if we think of beta is equal to 0, so sort of as small as it can possibly get, we're not actually thinking of beta as 0, but suppose it were, then that would tell us that our mu is 1 over zg for all sigma. So this is just the uniform distribution on all configurations. Each one is equally likely as every other one. And so that sort of tells us that there is some sort of randomness, some sort of disorder, I should say, going on here. Whereas if we're at a low temperature, which is large beta, we should think about it like a solid. And in fact, if we think about beta going to infinity, then our mu g of sigma, well, as we're increasing beta, then even having one more monochromatic edge will increase your probability by more and more. So as beta is going to infinity, what will happen is we're more and more likely to see the maximum weight configurations, and everything else will become negligible. So this will essentially be uniform on the maximum weight sigma, which will be the all monochromatic sigma. So all the so-called ground states where we have just all of the same color. And you can see that reflected here. We have one majority color, and we have very small defects from that majority color. But if I know that some particle over here is red, it's pretty likely that some particle all the way over here is also going to be red when we're in this low temperature regime. Okay, so this was sort of a heuristic, but can we formalize this notion? Oh, okay, so Mark has a question. Can I think of the energy term as how far my coloring is from being proper? So we're not considering proper colorings necessarily. I guess, yeah, I guess if you think about you're counting monochromatic edges, then with more monochromatic edges, you're farther from a proper coloring. So yeah, I guess that intuitively that is one way that you can think about it. One thing is that when we're thinking in the anti-ferromagnetic regime, then we're interested actually in minimizing the number of monochromatic edges. And so our ground states will become the proper colorings rather than the monochromatic colorings. But things get complicated in the anti-ferromagnetic regime, so I don't want to talk too much about that. But yeah, so hopefully that answered your question. Okay, so now I want to formalize this notion of like low temperature being sort of ordered and solid-like and high temperature being disordered and gas-like. And so how can I do that? So now I want to say a little bit about some work that I've done with several other co-authors. And so what I'll talk about now is joint work with Charlie Carlson, Ewan Davies, Nicolas Fraiman, Alexandra Kolla, and Aditya Potukuchi, which we put on the archive this year. And one of the results that we showed is a sort of structural result about the Potts model. And what we show sort of informally is that if we take D large enough and the number of colors to be some polynomial in D, then the Potts model on what I'll call deregular expander graphs has this structural phase transition that I was describing. And I'm not going to formally define expanders. And I won't go into too much detail about what those are, but if you're familiar with them, we're talking about expanders, including, for example, the discrete hypercube. So here we have two expanders, which means that the edge boundary of every set is at least 2 times the size of the set for all sets of vertices that have size at most n/2. So if you're familiar with the notion of expansion, then this is what we prove. And so in particular, QD, the discrete hypercube, falls in this for D large enough. Okay, so let me say what we say sort of more formally. Oh, and I should say before I say the formal statement that we show a phase transition, but with sort of a small gap around our critical values. So we have sort of high temperature arguments and low temperature arguments, and there is this little gap that is in a sense sort of expected about some of our methods. But it's our cost for getting a smaller Q. So previous results required Q to be exponential in D, and we were able to push it down to polynomial D, and in some regimes, even a constant. So even though poly D maybe doesn't seem too small to you, it's small comparatively. Okay, so here's what we actually show. So let G be deregular. Oh, I forgot that I had written it out here with edge expansion at least 2. When beta is smaller than 1 minus epsilon times some critical value beta naught, each color class is about the same size. It has size at most, n/q times 1 plus a little 1. When beta is large, there's a color class with at least half the vertices. So this is formalizing our idea of solid-like and gas-like. And this beta naught is something called the order disorder phase transition of the random deregular graph. And it's something like 2 log Q over D. Not super important, but it does have a precise definition that is asymptotically this. Okay, so this was our structural result. And it sort of reflects intuitively what we expect should happen. And what are the ingredients that we use in our proof? So what we do is we bound the number of Q colorings with exactly L non-monochromatic edges using an adaptation of Carter's algorithm for finding min cuts. So this isn't the only ingredient, but I sort of wanted to highlight this step because part of the proof, so the proof is, I'm not going to give you all the details. There are a lot of sort of fiddly details that I don't really want to talk about in a 45-minute talk. But I wanted to highlight this because Carter's algorithm is a randomized algorithm for finding a minimum cut in a graph. If you're familiar with it, fine. If you're not, that's okay. But it's something that is well studied in theoretical computer science. If you take an algorithms class, this is probably one of the first examples of a randomized algorithm that you would see. But we adapt this idea to prove what is basically a statistical physics result, about this sort of structural phase transition. And so since I can't give a talk without any proofs, I'll give you a sort of a short overview of this ingredient to the proof. And I'll say that some parts of it are exercises that you can check on your own time. Okay, so here's the lemma that we actually prove, which you can just state sort of standing alone. The number of Q colorings with exactly L non-monochromatic edges is at most this, where again, N is the number of vertices and we're deregular. And we're also assuming the expansion condition. And G is at least 2 expanding. So these are our assumptions. And I realize as I swipe, it's gonna go away, but you don't really need to remember these things. So here's the idea. We'll take sigma to be some coloring that satisfies this, a coloring with exactly L non-monochromatic edges. And what we're gonna do is we're gonna do some random algorithm and compute the probability that we recover sigma. So here's the random algorithm. So we repeat step 1 a bunch of times until we've shrunk our graph sufficiently. So we start with our big graph. We choose some uniformly random edge and we contract it. What that means is we just take the 2 vertices and we squish the edge into 1 vertex. And so every edge that was incident to one of the 2 becomes just incident to the new contracted vertex. And if there are any self loops, we just delete them. And so we keep doing this. We check our size of our graph, we contract, we pick an edge at random, contract it, check how big our graph is, pick another edge, contract it. We keep doing this until we're down to 2L over D vertices. And then when we're done, we do a random coloring, a uniform random coloring of the whole graph. And so when we have contracted our graph, we have some coloring. And from that, we can recover a coloring of the original graph, because if we have some edge that goes to a vertex and this becomes pink, then we can just say color both of those vertices pink in the original. Okay, and so what is the probability that when we have our final coloring and then we go back to a coloring of the original graph, we get exactly sigma, the thing that we wanted? Okay, so now here are the exercises. I'm just going to compute some probabilities. So this is an exercise. The probability that we don't lose any of the non-monochromatic edges. So we started with exactly L of them. What's the probability that we keep those L in the end? I claim that it's this number. And so this relies on the regularity assumption, and it relies on the expansion assumption. And in particular, what we need from the expansion assumption is that we have a minimum cut of size at least D. And so what that tells me is that as I sort of contract my edges, I can keep track of how many edges are in the graph as I'm contracting things. And counting those edges will give me these terms in the denominator. So what this is saying is that what's the probability that one of these edges does get contracted? Well, there are L of them. And then I just look at how many edges are in my graph at that step. So there are L edges, and this is the number of edges. I'll move this over. Oh, whoops, didn't mean to do that. In my current graph. So all of those denominators. And then I do, so that's a probability that one of the L edges does get contracted, and then I do 1 minus that, and I multiply all of these together. So, okay, if you know a little bit of probability and you know a little bit of graph theory, then this can be an exercise that you do. But if you don't, then you can just trust me that this is the probability. And if I sort of write out all these terms and compute it, I end up getting just 1 over n choose 2L over D. Okay, so that's the probability that I keep my non-monochromatic edges. And then I want to say, like, okay, those non-monochromatic edges, they got the correct color in step 2. Because if they weren't contracted, they would get those non-monochromatic edges would become monochromatic, which is bad for me. So I want to figure out if I can get them the correct color in my contracted coloring. Okay, and this is an easier exercise. This is exercise 2. The probability that every contracted vertex it gets the correct color is q to the minus 2L over D because I'm coloring each vertex uniformly at random. I end with 2L over D vertices. And so each of them has one color that I want, and there are q possible ways I could color it. So the probability, if I just look at both of my steps, the probability that I get the correct sigma is just multiplying this probability here with the probability on the previous slide. So that's this. And since this holds for any sigma, then I have at most this many Q colorings with L non-monochromatic edges. Okay, so these are all sort of exercises in probability. Okay, but if you've never seen Kargar's algorithm before, then this might give you a little bit of a sense of what is a randomized algorithm and how can we sort of analyze it and why is it useful for us. Okay. But if you didn't follow any of this, that's okay. There's sort of a main takeaway that I want you to have, which is a combinatorial perspective can help solve statistical physics problems. Because this lemma was ultimately a combinatorial sort of statement, but it ends up being a main ingredient that we use in our proof of this sort of phase transition result. Okay, so now I want to go to one sort of last type of problem still about the Potts model, and that has to do with counting and sampling. But before I do that, I'll pause for another awkward amount of time to see if there are any questions before I go on to one more type of problem. Okay, so again, feel free to ask things in the chat. So the last thing that I want to talk about are counting and sampling problems. And this is more of an algorithmic computer scientist perspective on statistical physics. So what do I mean by counting? I mean determining the partition function, because remember I said it was sort of a combinatorial way of like encoding different things about our spin models. And it's sort of a weighted count of these combinatorial things we're interested in. And sampling means sampling from the distribution, the probability distribution given by mu g. So it turns out that if we want to exactly determine this partition function or exactly sample, that is sharp p hard, meaning it's the counting problem associated with an NP hard problem. So it's pretty hard. So we won't have goals to sort of try and do exact things. But what if we just relax to approximate counting and sampling? Let's say I want some polynomial in beta that is close enough, like some epsilon distance away from my partition function. Or what if I want some distribution that's close in what's called total variation distance from mu g, and that's how you measure distance between probability distributions. Okay, well, there are three different sort of classes that spin systems on graphs fall into when it comes to this question of approximate counting and sampling. Some models have efficient algorithms for all graphs. For example, the ferromagnetic Ising model, that was with the two spins, do, but they're not necessarily deterministic. So one main question in this area is, can we get deterministic algorithms when what we have are randomized algorithms? Another class is models that are NP hard in general for general graphs, but there are efficient algorithms in some regime of parameters. For example, the hardcore model for some regime of lambda. And then the question here is, what is the algorithmic threshold? So this is another sort of phase transition we could talk about, but in an algorithmic sense, when do we switch over from having efficient algorithms to being NP hard? And the third question, which is the one I'll focus on for the Potts model, is some models that are somewhere in between. So this is a class of problems called sharp BIS, and BIS stands for a bipartite independent set. So this is the complexity of counting the number of independent sets in a bipartite graph. Independent set, so counting bipartite independent sets. And this is a complexity class that is, the complexity itself isn't known. It's not known whether it is strictly easier than NP hard or if it actually is NP hard. but it could lie somewhere sort of in between. And in particular, the ferromagnetic Potts model has complexity in this sharp bis range. And here the question is, what are the hard instances? Can we find some class of graphs or some regime of parameters where we do have efficient algorithms? And then narrowing that down will allow us to better understand what exactly is the complexity of sharp bis. So another result that I want to highlight is a result exactly how I described. We find a class of graphs and a range of temperatures where we do find polynomial time approximate counting and sampling algorithms for the Potts model. And the class of graphs, again, are D-regular two expander graphs, and the set of temperatures are all temperatures, but with a small gap around the critical value beta naught. And as I mentioned earlier, this Q equals poly D is a significant improvement. We can compare it directly to Jensen, Kivash, and Perkins. They managed to get around having this gap, but they required Q to be exponential in D, and they required, some function of D, sort of expansion in the low temperature range. Okay, so the takeaway from this is that actually we not only can use tools from one area to solve problems in the other, but we can actually get new and interesting questions in both areas by taking the two different perspectives. Because without computer scientists, I don't think statistical physicists would have asked this question about approximate counting and sampling. And without statistical physics, we wouldn't have had this context to analyze this complexity class of sharp bis in the theoretical computer science area. Okay, and I know I have only a couple of minutes left. And so I wanted to give a very quick and dirty overview of the ideas of our proof, because we use a combination of tools from all the three different areas: statistical physics, combinatorics, and algorithms. So the algorithms part is a repeat sort of what I said earlier about the randomized Carter algorithm for min-cut. But here's a sort of, a very vague set of steps for what we do in the low temperature regime to find efficient algorithms. So the first thing we do is we remember that low temperature is we want to show that basically everything is like a solid, that most of the weight is coming from monochromatic or close to monochromatic colorings. So what we do is we characterize our colorings based on their defects from the monochromatic states. And we want to argue, we essentially argue that we can only consider colorings with small defects. Anything with a large defect is not going to contribute very much weight to our partition function. And we define something called an abstract polymer model, which is a tool used in statistical physics that has the same partition function as the one we want. And so what this allows us to do is sort of put in a black box the different tools that you can use for abstract polymer models, because if we can approximate this polymer model partition function, then that gives us an approximation of the partition function we wanted. And then structurally, we show that most of the weight in this polymer model partition function is from the colorings with a majority color. And algorithmically, to get our efficient algorithms, we show that this polymer model partition function satisfies something called the Katetsky price condition. And once we know it satisfies this condition, we know that we have something called convergence of the cluster expansion, which is a fancy way of saying it's the Taylor series for the logarithm of the partition function. So just what you know from calculus Taylor series, but we can write it in a really nice combinatorial way, and that's called the cluster expansion. And other people have then done the work sort of beyond this point. In particular, Helmuth, Perkins, and Regst in 2019 were the first people to show that in this very abstract general setup, we once you know that your polymer model satisfies certain conditions, here is how you get efficient algorithms by computing coefficients of this cluster expansion. The approximation that we use is essentially a truncation of the Taylor series. And we say okay, the tail of the Taylor series, doesn't have that much weight. And if we truncate at a certain point, that's a good enough approximation for our polynomial. Okay, and that's sort of all the detail that I wanted to give in this proof. And I just wanted to mention that I have focused on a few different examples, and in particular, since there's a project that I personally worked on, I wanted to highlight the Potts model and these algorithmic questions, but there are many more ways that statistical mechanics interacts with combinatorics that I haven't even touched on. In particular, things about Markov chains and mixing times are very closely related to this question of efficient algorithms. Things in percolation theory, and you can generalize percolation to something called the random cluster model, which is then a generalization of the Potts model. So those are also very closely related. There are things called exactly solvable models, like the square ice and the 8-vertex model, which are very well studied more so by algebraists and physicists. There are continuous models, like the hard sphere model that I briefly mentioned as sort of the motivation for the hardcore model earlier, and much more. So I hope that, at least in this talk, I gave you a little bit of a sense of the questions that I personally find interesting as a combinatorialist. But I encourage you to sort of look into the great breadth of statistical mechanics and see if there are any problems in these intersections that interest you as well. Okay, so I'm out of time, so I'll end there. Thank you very much for your attention.
Okay, please join me in thanking Corrine for a wonderful talk. Do we have any questions from the audience? I have a question, but it's not particularly combinatorial, rather a lot more statistical. So I might let the combinatorics come first, given that that's the point of this symposium. So I'll give a minute or two for people to type out any questions that they have. So we have a question from Mark. I have two questions. The first is, when I plug in E for I in the coloring lemma, I get an upper bound for my proper colorings. How good is it?
I don't know what you mean when you say when you plug in E for.
Or is that L?
I.
Is that
E for L.
Capital L. I. Yeah, that makes more sense.
Number of edges for L. Oh, I see. So if you're saying that every edge in your graph is non-monochromatic, then what happens with this bound? Okay. I don't know off the top of my head how good this algorithm is. So if you plug in like the maximum possible value you could get into L, my sort of naive guess with that is that it might be rather wasteful. But I don't know. I guess I have not ever thought about how to cleverly count the number of proper colorings of a graph. And so I don't know if necessarily the random way of going about it is going to be close to the truth. So yeah, I would be interested in hearing about that, but I wouldn't say off the top of my head what the correct answer should be. So I have to say I haven't thought about this question before, but that is an interesting question. Yeah.
Okay, was that just one of two questions, Mark, or was your two questions joined together there? Maybe in the meantime, we've got a question from Angus. You mentioned you assumed regularity of the graphs since it gives you lots of edges. What if you just assume that G is a sufficiently dense expander graph, but not necessarily regular? Do things still work, or is regularity important?
That's a really great question. So our motivation for thinking about regular expander graphs was because we initially just wanted to tackle the discrete hypercube. And so of course that's a deregular expander graph. And so we just generalized what we had. I would say that when you stop thinking about regularity, the next sort of natural thing to think about is just, or sort of the other natural class to think about is bounded degree graphs. And those are also interesting in many contexts. For our particular methods, I do think that regularity ends up playing an important part, in particular because we use a lot of combinatorial tools that I didn't mention here, that are, if you're familiar with container lemmas from hypergraphs, then we use some sort of container type lemmas to count the number of sets with a given boundary size. And for those estimates that we do, we use the regularity pretty heavily. And you could substitute a maximum degree for that regularity for whatever you use for regularity instead, and it would still work out. But if you don't have bounded degree, then I wouldn't quite know how to approach the sort of, or how to use the sort of combinatorial tools that we use.
Okay, and we also have a question from Peter Bradshaw on slide 16. Could you talk more about alpha?
Okay, slide 16. Hopefully that's slide 16 in this direction. But if not, I'll go back to page 16. No, okay, slide 16, meaning in my number of pages in my notability, I think. Is that right? I'm trying to think of where I used alpha. Let me see if I can
page
move
16,
this.
Peter has.
Okay. Great. Okay, I was trying to open that. Here we go. Yes, okay. So this is something, alpha is something called the occupancy fraction of the hardcore model. And it's essentially something that if you look at the expected size of an independent set, and then you normalize that by the number of vertices. Another sort of clever way of doing this is something called the occupancy method. So that's why it's called the occupancy fraction. Occupancy method. You look at the sort of expected size of your independent set and you divide by the number of vertices. And it turns out that this alpha, you can relate it to the derivative. It is the derivative of the log of the partition function, I believe. I think that's right, maybe divided by n. So that's another nice exercise. Alpha is equal to the derivative of the log of partition function with respect to lambda, maybe over n or something. And so this sort of perspective on the hardcore model was the basis of this entire paper called, that has to do with this thing called the occupancy method and using linear programming to actually prove this conjecture. So that was another sort of innovative technique that was brought into this conversation.
Okay, thank you. And Mark has typed out his second question. For the partition function of the Potts model, if you take the partition function of the disjoint union of graphs, is it just the product of partition functions of each component?
Yes. Well, I said that too quickly because I was still thinking about the hardcore model. For the hardcore model, certainly. For the Potts model, you're looking at, let's see, the weighted sum of colorings. I believe so, but I haven't thought about it, so I'd have to write it out. But yeah, I think we for the most part only assume connected graphs because in general, in the spin systems that we work with, then if you consider different components, then you're just taking products of partition functions. But yeah, I can't do the math in my head right now. I'm trying to think about multiplying these different weights. And the exponents might pose a problem because you're multiplying this e to the some beta times e to the some other beta. You get the number of monochromatic edges. I want to say yes, but I would have to like make sure, sit down and do some calculations to make sure.
Okay, thank you. Mark has contributed.
Yeah, that's what I'm thinking. I just don't want to like say something that I haven't like sat down and written out.
Yeah, Okay. My question was more to do with something you touched on at the end briefly about Markov processes involved.
Sure.
Has there been a lot of research in this? I know that these Gibbs measures are very like explicitly, Bayesian kind of statements. It seems like you should be able to come up with some sort of like Metropolis Hastings kind of sampling. Sort of sampling out of this.
Yeah, absolutely. There's something that's well studied called the Glauber dynamics of a model, where it's single spin changes. So you start with some configuration, you pick a vertex uniformly at random, and you resample its spin, just conditioned on the distribution of its neighbors. So for example, for the Potts model, you recolor. And this gives you sort of a one-step process that you can model as a Markov chain. And these questions about finding efficient algorithms, you can reword them in terms of fast or slow mixing of this Markov chain. And so there's a lot of research that looks at the different ways you can use these dynamics to define these Markov chain processes and whether you have fast or slow mixing in certain regimes. So yeah, it is definitely a very well-studied area that there's still a lot of sort of progress like currently being made and problems that are still being explored. Yeah.
Cool, sounds very interesting. Thank you. I haven't seen any more questions pop up in the chat or Q&A, so I assume we're good there. I might stop the recording. But can we just give one more round of applause to Corrine for a wonderful talk?
Thank you so much. Thank you.